Hi everyone. So my name is Alex, and if you're looking at this, you probably actually know who I am. So in particular, you might have noticed that when I was a naive first-year grad student, I decided I would try to uh, record an interesting physics problem every week and post it online, and that obviously failed miserably, seeing as I got about 7 of them done, and then kind of ran out of time. Well, so this semester I'm actually studying for my Part 3 qualifying exam. So at MIT Physics here we have 3 rounds of qualifying exams, and I'm getting ready to take the third one, and it's an oral exam. It's a 2-hour oral exam on our specialty. So I thought one of the things that they give us as a study guide is a list of 180 questions about astrophysics, and I thought, you know, it would be cool if I recorded some subset of these, just, basically for my own benefit to make me practice talking and writing at the same time, which is, as everyone knows, is very difficult. Um, and hopefully maybe someone else might find it interesting, but really this is just for me to, this is really for my own benefit. So unlike last time, I'm going to not even really bother trying to make it nice or fancy or good. So yeah, so today I'm going to start with the first question. Let's see, let me just load this really quick to see if it's working. Okay, great. So today I'm going to start with the first question, which is how did the Greeks determine the size of the Earth and the distance to the moon? So there's 2 questions here, and they were actually done by different people. So I'm going to first start with how the Greeks determined the size of the Earth by drawing an Earth over here. So if you have a circle, which is a cross-section of the Earth, and you know that there's some distance across here, let's call that d, and you know that there's some angle, theta, then you can measure the radius of the Earth because d is equal to r theta. So what you have to do then is simply figure out a way to measure d and a way to measure theta. So measuring d is not too hard because basically you pick 2 points and then you send someone from one side to the other, and you just kind of walk from one way to the other, and maybe, I don't know, you like figure out how big each of your steps is, and count how many steps you take in a day, and you have to travel some pretty long distance in order to get a decent theta, but you can do it. And there was a guy in Greece who did it. I think actually he was living in Alexandria. Anyway, so that's the first thing. The second thing is, if you let's assume that the sun is over here on the right. That's our sun, and it shoots parallel light rays over towards the Earth. Then you can measure the angle theta by taking advantage of the fact that these light rays are parallel. So I'm going to draw the angle over here, and this is kind of the normal. So if the sphere is big enough, you can approximate that as flat, right? That's actually the kind of curvature. And we have our light rays coming in over here. So this is parallel, and here's another angle, and here's the other parallel ray, and yet here is another parallel ray, and I'll zoom in on that section in a second. So this angle theta, because these rays are parallel, you can actually use the various geometric parallel line things, and in particular, if you have some object that's kind of sticking out of the ground over here at a right angle to the ground, if you have these parallel rays, I have this angle theta, and this thing is over here, then what we'll do, and here's kind of like land, then this region over here that I'm shading in is going to become a shadow. And you can measure, if you notice, this angle is theta, but this angle over here is also theta. That didn't come out very well. That angle over there is also theta because these lines are parallel, because they're both coming from the sun. So since this is a right angle, what you can do is you can just basically use trigonometry, which the Greeks did kind of know about, to measure this angle. So you have this tower, it casts a shadow, use the shadow and the height of the tower or a stick or whatever to measure this angle theta. And then you just simply do r is equal to d over theta. Of course, you have to measure theta in radians here. If you turn it into, you have to, if you measure it in degrees, like they probably would have, then you turn it into radians by just multiplying by pi over 180. Okay, great. So that's actually fairly straightforward. So let's move on to the next one, which is figuring out the distance to the moon, which is actually kind of difficult. And I actually did this once, then realized I didn't actually know how to solve the problem. So here it is again. So the basic idea is we're going to take advantage of the fact that there are eclipses going on. And so if you have a sun over here, you've got like a little Earth over here, you've got a little moon, kind of circling around the Earth. So that wasn't a very good circle. Let me redraw that. Okay, so it's just kind of circling around. Then there's kind of two interesting points that could happen. The first one is that it can be aligned such that the moon is kind of covering up the sun, in which case you have a solar eclipse. Or alternatively, the Earth can actually be covering up the moon, so at nighttime, the moon will actually go dark for a little bit because the Earth blocks the sunlight that normally reflects off the moon. So using these two facts and the fact that when you look in the sky, the moon and the sun look kind of the same. They look the same size. They're the same angular size. So using this, we can actually figure out the distance to the moon. So I'll draw the first thing, which is that if that's the sun and this is the Earth, then the sun will cast kind of a shadow. Or, sorry, the Earth will cast a shadow by blocking the sun. And there's kind of this dark region over here that's conical shaped because the Earth is a sphere. And so inside of that cone is kind of the place where you get a lunar eclipse going on. And so if you actually go and measure what happens during a lunar eclipse as the moon kind of travels through this here, you'll see that the Greeks actually went out and measured this during a lunar eclipse, and what they found is that so if this is kind of like the diameter, so if this is the radius of the Earth, and this is some length L, I'm just going to use the upper half of the triangle, right, of this little thing. Then they found that the moon was basically completely dark for about 2.5 times its diameter. So basically, if you have a ball and it goes past here, based on how long the moon is dark for, you can figure out the ratio between this L and the radius of the moon. Okay, great. So as I was saying before, what you can do is when you have a lunar eclipse, you can actually measure the difference between the ratio between this RM, which is the radius of the moon, and L, which is the kind of the distance that the distance that the moon is covered for inside of this shadow. And so this is going to be really cool because we're going to be able to get some really nice similar triangles to solve for just absolutely everything. Okay, so the first thing is we can figure out all of these things. So let's imagine this is kind of like the radius of the sun. And let's imagine this is the radius of the Earth. This is totally not the scale, but then there's kind of two ways you can take advantage of this. The first thing is that, like, if you this angle over here, which I'm going to call alpha, you can actually measure this by kind of holding up a coin. So if you use a coin and you figure out the distance at which you have to hold it so that it will cover up the sun, then you can actually measure this angle alpha. So let's call this distance over here R coin, and this one D coin. then you just have the tangent of alpha is equal to r coin over d coin. And that's actually pretty cool, because you can actually just measure this like standing on Earth. So you know this angle alpha, which is the ratio between the, the radius of the sun and the distance to the sun. But that's also the same. That triangle over here is actually the same. It's a similar triangle to this triangle over here, where you use the radius of the Earth, and you use this distance as the shadow that it casts. This alpha is the same. So I'm going to call this distance over here d shadow. Okay, so that's super cool. So this in some ways gives you an upper bound. This is d shadow. It goes all the way out to here. This kind of gives you an upper bound on the distance of the moon, because if it's beyond here, like if the moon was out here beyond this shadow distance, then you wouldn't be able to get an eclipse, right? You wouldn't have this total eclipse of the moon, this lunar eclipse. So that's kind of an upper bound, and you can calculate d shadow. I guess tan alpha, and we know alpha is equal to RE over d shadow. So d shadow is equal to RE over tan alpha. Where if you want, you can just plug this in to figure out what tan alpha is. So that's cool. That gives us an upper bound on the distance of the moon, and now we're going to utilize this other fact, which is the fact that the moon and the sun are the same angular size, which means that you can actually also put this r moon and look at this triangle over here, and that also has the same alpha. And then down here, this is d moon. So that's super cool, right? Because that means r moon over d moon is equal to RE over d shadow. And now we have to use some extra bit of information here, which is that you have this L. I'll call this over here. Let's call that D. Well, I won't call that D because we can actually write it in terms of other stuff that we care about. So this over here, up until that point, is d moon, and the entire thing is d shadow. So that means that L over d shadow minus d moon. It's kind of hard to write over here. So L over d shadow minus d moon is also equal to this over here. It's all part of the same similar triangle, right? It's super cool. And it kind of takes advantage of this coincidence that the sun and the moon are kind of the same angular size. Okay. Great. So now what we can do then is we can basically just take this equation and solve. And oh, sorry, I should add one more piece of information. We know that L is equal to 2.5 times the diameter of the moon, so it's actually 5 times the radius of the moon. Sorry, this is actually 2.5. Yeah, my bad. Okay, great. So we can just cross out that L, and now we have 2.5, our moon up here. And so now we can actually just eliminate our moon by looking at this guy and this guy, right? So that means 1 over d moon is equal to 2.5 over d shadow minus d moon. You cross multiply, you get d shadow is equal to, I'll add it over, so you get 3.5 d moon. So now we just plug this in over here, and d moon is equal to 1 over 3.5 times d shadow, which is the radius of the Earth, and then divided by this tan alpha, which you can measure using just the coin. So that's it. That's awesome. Okay, great. So that's it. I'm gonna try and record at least 5 of these a week, just because there's a ton of questions, and I want to, they're gonna be of varying quality, because I'm just gonna sit down and start talking. Hopefully, it will be questions which I know the answer to, so I don't sit and blather for a while. But um, yeah, I should know the answers to these questions. So that's great. So um, so that's it. I'll have to do some video editing to clip those guys together, but that's probably good for me to learn as well. Great, thanks.